Assalamualaikum. Good morning. Namaste. Sat Sri Akal. Buenos dias. My name is Raja Salim Akhtar. Presently, I am living and working in Barcelona, Spain. Welcome in the class of M.Sc. Mathematics, chapter Motion of Rigid Bodies, in 3 dimensions. In this chapter, we shall study the following topics. Number 1, general motion of rigid bodies in space, moments and products of inertia, Inertia Matrix. Number 2, the momental ellipsoid, and equimomental systems. Number 3, angular momentum vector, and rotational kinetic energy. Number 4, principal axis, and principal moments of inertia. Number 5, determination of principal axis by diagonalizing the inertia matrix. Topic 1, general motion. Of rigid body in space, moments and products of inertia, inertia matrix. We consider a rigid body. This is an arbitrary axis about which this rigid body is rotates. This is the axis of rotation. We consider an ith particle of mass mi, which is perpendicular to the axis of rotation. We consider point O as the fixed point through which coordinate axes pass. This is x-axis, this is y-axis, this is x-axis, and this is z-axis. Arbitrary axis of rotation makes angle alpha with x-axis, angle beta with y-axis, and angle gamma with z-axis. This is the origin O. Let Ri denote the position of ith particle. This is perpendicular distance of ith particle from the arbitrary axis. There is a unit vector n along the arbitrary axis which makes angle theta with position vector Ri. The velocity of the ith particle will be along the tangent Vi, and this is perpendicular to the perpendicular. (90°). This is also 90°. We shall calculate the moment of inertia state the moments of inertia of a rigid body about an arbitrary axis which passes through a fixed point. Fixed point O. Let omega is the angular velocity and n is the unit vector along the arbitrary axis of rotation let alpha, beta, gamma are the angles that the angular velocity vector W omega makes with the fixed coordinate system to the rigid body which rotates with it. Consider the ith particle of mass Mi which is at the perpendicular distance or prep I from the arbitrary axis of rotation. Let theta I is the angle between position vector Ri of the ith particle and unit vector n. Let Ri vector is equal to xi, I unit vector, yi, j unit vector, plus zi k unit vector is the position vector of the ith particle. Let direction cosines of the arbitrary axis of rotation are cos alpha, cos beta, cos gamma. Therefore, n unit vector will be equal to cos alpha I unit vector plus cos beta j unit vector plus cos gamma k unit vector. Now, by definition of moment of inertia, in this case we have I is equal to sigma I mi or prep I square. Mass into square of the perpendicular distance of the ith particle from the arbitrary axis. You can see it in the figure. Now, as clear from the figure, you can see from the triangle or prep I equal to magnitude Ri sin theta I. This is equal to magnitude Ri vector cross n unit vector magnitude. This implies R prep I square equal to Ri vector cross n unit vector magnitude square. Now, the cross product of two vectors magnitude into I j k, component of the position vector are I, xi, yi, zi, and cos alpha of n, cos beta, cos gamma magnitude square. After expanding, square root will be cancelled with square. We have yi cos alpha minus zi cos beta I square minus minus plus plus zi cos alpha minus xi cos gamma square plus xi cos beta minus yi cos gamma whole square. After simplification, we get yi square plus zi square into cos square alpha plus zi square plus xi square cos square beta plus xi square plus yi square into cos square gamma minus 2yi zi cos beta cos gamma minus 2zi xi cos gamma cos alpha minus 2xi yi cos alpha cos beta. Now moment of inertia I equal to summation I mi r prep I square equal to summation I mi yi square plus zi square cos square alpha plus sigma I mi zi square plus xi square cos square beta plus sigma I mi into xi square plus yi square cos square gamma minus 2 into sigma I mi yi zi cos beta cos gamma minus 2 into sigma I mi zi xi cos gamma cos alpha minus 2 sigma I mi xi yi cos alpha cos beta. This can be written as moment of inertia I is equal to Ixx cos square alpha plus Iyy cos square beta plus Izz cos square gamma plus 2 Iyz cos beta cos gamma plus 2Izx cos gamma cos alpha plus 2Ixy cos alpha cos beta. Equation 1, where Ixx equal to summation I mi yi square plus zi square. This is moment of inertia about x-axis Iyy equal to sigma I mi zi square plus xi square. Moment of inertia about y-axis Izz equal to sigma I mi xi square plus yi square. This is moment of inertia about z-axis, and Ixy is symmetric. Iyx is equal to minus sigma I mi xi yi. This is xy product of inertia. Similarly, iyz, izx equal to minus sigma I mi yi zi yz product of inertia. I is equal to izx equal to ixz equal to minus sigma I mi zi xi. This is zx product of inertia. Note the minus sign. Which can be ignored. For the rigid body, we replace the summations by integrations. Therefore, moment of inertia Ixx equal to integral x square plus y square into dm. Iyy is equal to integral z square plus x square into dm. Izz is equal to integral x square x square plus z square, and this is x square plus y square into dm, and ixy iyx is equal to minus integral xy dm iyz equal to izx equal to minus integral yz dm izx moment of inertia ixz equal to minus integral zx dm. Then equation 1 is called moment of inertia of a rigid body in space about an arbitrary axis of rotation. Now, equation 1 can also be written as I is equal to matrix cos alpha cos beta cos gamma ixx ixy ixz iyx iyy iyz izx izy izz. Cos alpha cos beta cos gamma. This is equal to n transpose capital I in boldface letters into n unit vector where nt means n transpose. Transpose and I is equal to ixx ixy ixz iyy iyx iyy iyz izx izy izz is called inertia matrix or the moment of the inertia tensor. Hence, more compact form of the moment of inertia of a rigid body in space about an arbitrary axis is I is equal to n transpose inertia matrix capital I in bold form and n.